This is video number 3 for sections 9.3 and 9.4, radical functions. For a lot of the semester, we really concentrated on functions and their graphs, different types. We don't really have time left to get into great detail with radical functions. This is just a little bit of introduction. In fact, we won't even talk about anything except basic square root functions. So let's say we created this extremely basic function f of x equals square root of x. Let's play around with that a little bit and see what that looks like. First thing I think I'll do is make a table. So I'll pick some x's and stick them in here. And then we'll go through and let's figure out the corresponding y value. We just need to plug right into the function. And obviously it's pretty simple. Every time we just need to take the square root of that x value. Of course, when you try to do that with -1, you realize I can't, right? That's impossible. So there are certain types of x's that you can't even stick into this function. Maybe you're thinking of imaginary numbers, the whole I thing. But when you're talking about functions and graphs, you're only talking about real numbers. So the I stuff does not apply. I cannot stick -1 into this function. How about 0? That I can do. Square root of 0 would just be 0. And let's see, how about 1? Sure, square root of 1 would be 1. Now after that, you kind of realize, maybe 2 is not the best number to plug into this thing if I'm trying to do this quickly by hand, because square root of 2 is not a particularly nice answer. What would be the next nice x I could use? I guess it would be 4, because the square root of 4 has a nice answer, namely 2. And then after that, it would be 9, because the square root of 9 has a nice answer. So just a quick table there. And obviously, I could fill in other values using a calculator. Let's take these values and plot the points and see what the graph of a square root function looks like. So I'll start with 0, 0. And then I've got 1, comma 1. And 4, comma 2. And 9, comma 3. That's about all I have room for. And then I'll connect the dots, and so I get something that looks kind of like this. I will not put an arrow at the other end. I know that this thing just stops here, because when we tried to plug a negative value in earlier, it was not possible. There's just no way you can have any graph over here where all the negative x's are. But of course, over to the right, it must keep going. I could plug in lots of numbers that are bigger than 9. I don't know if you recognize this shape that I have just drawn. It is a shape that we have seen before. You might have to turn your head to the side, but it's basically just half a parabola. And that's exactly what it is. It's half a parabola. It shouldn't be surprising, because of course the square root function is related to the squared function, x squared, which is a full parabola. So square root function is this half parabola kind of lying on its side. Let's answer the next part. What's the domain and range of this function? You can see this information right off the graph. Domain would be the list of all x's that you could ever use. Well, we pretty much talked about that. You can't use negatives. Those are off limits, but you can use 0 and above. So anything greater than or equal to 0. The range we have not really talked about, but we can see it off the graph. What's the lowest y value on this graph? Well, again, it appears to be 0. There's no negative y's, but 0 and higher show up on the graph. So the range is essentially the same thing, all y values that are greater than or equal to 0. So that's kind of the basic square root function. In application problems, and I'll do one next, all that's going to happen is the equation is going to be tweaked a little bit and the graph is going to be tweaked a little bit, but the ideas are going to remain basically the same. So let's take a look at one example problem. Again, we're keeping this pretty simple because we don't have a lot of time to get too deep. This problem says we've got a company and they have been keeping track of their profits, okay, for a variety of years. And the idea here is they took their profit information, they graphed a scattergram, they looked at the pattern, it kind of looked like a square root function, and so they figured out, oh, here's an equation that we can use that models our profits over various years. And pay attention to the variable definition. It looks like the profits are being measured in millions of dollars, and the T variable stands for years since 2010. So we got to keep that in mind. Okay, let's try to work with this a little bit. So part A, find f of 16. That's just a math problem. Take the 16, replace all the t's with 16. This is obviously something I can work out by hand because square root of 16 has a nice answer, namely 4. And when you work out the math here, you're going to get 11. 8 plus 3 is 11. So f of 16 is equal to 11. And then it says, well, what does that mean in terms of this real life scenario? So let's try to write a little sentence. We need to take into account both the 16 as well as the 11. Well, the 16 is a T. T stood for how many years it's been since 2010. So if T is 16, that would be the year 2026. So we're learning something about the year 2026. In 2026, this company will make, and then the 11 refers to the other variable in this problem, the output variable, which is the P, the profits. We'll make a profit of, don't say $11, remember it's measured in millions of dollars, so $11 million. We've done this sort of thing many, many times. Now we're just doing it with another type of function, this radical function. Let's take that function and draw a graph. And maybe it would be helpful if I copy the function down here. If we want to make a graph, probably a quick table is our best bet. And kind of like that earlier table that we made, if I just pick relatively easy values for t, then I can probably get a pretty fast picture up. So 0 worked pretty well before, 1 was great, 4 and 9, kind of those perfect square numbers because I can so easily stick them here in the square root. So square root of 0 is 0, times 2 is still 0, plus 3 would be 3. Square root of 1 is 1, times 2 is 2, plus 3 would be 5. Let's see, then it starts to get a little bit more complicated. So if I plug the 4 in, what's going to happen? 2 root 4 plus 3. So square root of 4 is 2, times 2 is 4, plus 3 is 7. And if I plug in the 9, I get 3 times 2 is 6, plus 3 is 9. So that's a good handful of points. 0, 3, 1, 5, 4, going with 7, and then 9 way out here going with 9. And when I connect the dots, I don't get exactly the same graph that I had a moment ago. It's just a variation of it. It still has that basically same shape, the arrow off to the right, the stopping point here at the left side. This would be a picture of this company's profits. Let's go ahead and match this on the TI and make sure it looks the same. Okay, so I've got the calculator up. Let me go to the y equals area and I will type in the equation 2 and then the square root button over here on the left. We'll have to use x. Let me arrow out of the square root. Be careful with that kind of stuff. 2 root x plus 3. And I'll try to make my window look like the one that was on the paper. So the paper went from about x equals -9 to 9, counting by ones. And then the y values went from -7 to 10, counting by 1. So I think I'm all set. And I'll hit graph, and I'm just expecting to see similar to what I had. It's interesting, you'll notice the technology with stopping points and things like that sometimes can be a little misleading. I would say from this picture it's a little unclear, isn't it, that this thing goes through the point 0, 3. We absolutely know that it does. In fact, if I hit trace and 0 and hit enter, it will definitely take me to 0, comma 3, but you can see the technology is sometimes a little limited, so knowing how to do these things by hand is important. Okay, so back on the handout, let's finish this off. We're being asked once again to state the domain and the range. For the variables, I should not use x and y. I have t and I have p in this problem, so the domain would be all the values of t that I could stick in. You can see it right from the graph, no negatives once again, so the domain would be only 0 and higher. And then the range, well, let's see, I just need to look at the lowest y value, the lowest p value, I guess, so to speak, is clearly 3. There's nothing below 3. So it looks like I only have p's that are bigger than or equal to 3 on this graph. There would be the range. Okay, let's finish it off with using the equation to answer a question. And here was the equation again. The question said, what is the company's profit this year? Well, obviously, as you're looking at this, it depends on what year you're watching this video. I'm making it in 2020, so I will use the year 2020 to demonstrate. In order to answer this question, I do need to go back and refresh my memory as to the variable definitions. Remember, T stood for years since 2010. I'm always needing that starting year, right? So if I want to answer a question about 2020, I'm going to have to think, well, what value of t should I put in? And that's going to be, of course, 10. So I just need to plug 10 into this function and I'll be all set. F of 10 would mean what's the profit 10 years after 2010, in other words, in 2020. The equation is 2 root t plus 3. So when I plug 10 in, that would be 2 times the square root of 10 and plus 3. Root 10 is not a nice answer, so I don't really have any choice except to go to my calculator and work this out. And when I do that, I get about 9.3. It says to round to 1 decimal place. What are we saying here? We're not saying $9.30, right? Because P, the output value, is measured in millions of dollars. So we are saying in 2020, we're expecting the profit would be 9.3 million. And that would be the answer. I hope what you're seeing is that so much of what we've learned all throughout the semester can be applied to many, many, many different kinds of situations. Once you learn the tools, you can use them all over the place.